Hello, welcome to the final class about a paper of Terence Tao about the Collatz Conjecture. So in this class we'll prove the proposition and what's left to be proven, and it's going to be quite technical, but we're going to get to the very core of the argument, which is a kind of a renewal process, which you will see. Okay, so first of all, let me just recall you what was the proposition left to be proven. And this is the following. So we need to show the following. Which I call proposition 28. Which is the following. If I define Fn of L to be the probability of the Syracuse and so this will be a random variable, which I will call in a moment. So we define this sequence like this for L in Z mod 3 to the Zn, mod 3 to the Nz. So if I define this, then if 1 is less or equal than m is less or equal than n, and A is any positive quantity, and we have that the oscillation Mn of the sequence Fn decays power-like. It's M, sorry. Yeah, this is M. Okay, so this was the proposition we were left to prove. And then, so this, the proof of this is carried out in section 6 and 7 in his paper. So I can prove that back. Okay. And as a reading exercise, a reading problem, since I'm reading all these papers, I will give you a reading problem, which is read section 6 of Tao's paper. So reading in this part, there isn't any kind of a much clever kind of a proof or argument. It's just a reduction. So it's just in this section he would just reduce proposition 28, which reduces proposition 28 to. And be aware that, well, I can't use exactly the notation he's using because it would not be helpful in classes like this on the boards. I'm using kind of a slightly different notation, so be aware that you will see some different notations here that you have to figure out the dictionary between my notation and his notation. It's not that much differences, but there are some differences. So, which reduces proposition 28 to proposition 29, which I will state now. So that's your problem. So this is section 6 in proposition 29, which I will state now is proven in section 7, which is what I'm going to do in this lecture. So what's proposition 29? He calls it the decay of characteristic function. And actually, later he mentions that this 29 is actually equivalent to 28. Okay. So proposition 29 is the following. Let n be greater or equal to 1. Xi be some residue class which is not divisible by 3. Not multiple of 3. Okay, so it's not congruent to 0 mod 3. Then the expectation of e to minus 2 pi I xi Syracuse n divided by 3 to the n decays polynomial like. Okay. For every positive eddy, we have this. So proposition 29 implies proposition 28, and that's your reading exercise here. And thinking in yeah. Yeah, so in Tao's paper we'll have different numbers, of course, but we can figure out. Okay, so basically we're going to prove this thing. And now I just want to recall some facts about probability. But before that, let me just remind you what is Syracuse. Syracuse n is just that function fn, which was involved in the calculation of the n iterate of the S map, the speed up of Syracuse, the Collatz map, by applying the random variable, the random vector, geom to the n, and then I do mod 3n. And recall that I extended mod 3n to be also, because this function here has values in this function here has values in z a half, and when I do mod 3n, I identify the inverse powers of a half of R2 with the idea is to identify 2 with the inverse to the L, with the inverse of 2 to the L mod 3n. Okay, that's the identification. That was the mod n, and I'm going to use this definition of mod n, this extension of mod 3n for all during all the class, this lecture. Okay. So recall the following. So recall, I did define what is expectation of a random variable, that you know. But I will be dealing with conditional expectation. I don't remember if I defined what conditional expectation. So this is conditional expectation of a random variable x, and by definition is just if you go back to the probability, to the sample space or the event space, that would be just the integral over this condition to this event A, and you divide by the probability of the event. Okay. So what else? We can also, so suppose I have like a sequence x1, x2, and so on of independent and identically distributed random variables, you can compute things like the expectation of, let's say, x1, x2, restricted to the event that x2 plus x3 belongs to S. You can compute things like this. So we can compute like this, and this is to be computed in a product space. So you have to, so if each one of these random variables xi has an associated sample space with a certain probability measure pi, let's say, then you have to go to the product space, let's say omega infinity, which will be the proper product of these things up to infinity, and the probability measure you put in there, let's say p infinity. If you have a product of sets which contain, let's say, up to Sn, and from that point on you just have all the spaces, the full spaces. So a probability with this would just be the product of the probability I of the Si from I equals 1 to n. Okay, so that in this way you can define a proper measure, that's extending this to the sigma algebra, etc. So just recalling stuff here. You can define a probability in the product space, and things like this have to be computed there. Okay, this is basics of probability theory. So we can compute things like this, and they should be computed in the product space. Okay. And another thing, a common trick we're going to be using all the time here, just switch to this one, is the following. So this will be like +1, 2. So a common trick we'll be using all the time is to iterate an expectation. So suppose you have like an expectation of some function f of a bunch of random variables. And in this case, they don't need to be identically distributed. What you can do is you can compute the expectation of, let's say, q of x1, okay, where q, so suppose that x1 up to xn are all, let's say, so let's say each xi is k valued. Well, k can be like a residue class in a higher dimensional space, or it can be the real, the complex number, etc., whatever. So you define k of q to be the expectation of f of q, and then all the other ones. And then if you do the expectation of this function applied in x1, that will be the original expectation. So this will be, so you could say in principle that this thing here is the expectation of the expectation of the function k x2 xn when k is x1. You could say something, some sort of thing. So you could imagine this as being an expectation of an expectation. You can iterate this procedure if you like. Okay, so this will be a trick we'll be using a lot. Not trick, but this is something almost standard if you're using probabilities. If you have a probabilistic argument, you will use this kind of stuff all the time. Okay, so let's move to the proof of proposition 29, and that would take us to a long ride. So this will need a series of observations, lemmas, and calculations to get to the end. Okay. And the basic idea is to consider a certain kind of a random walk or a renewal process, and try to understand what happens when this random walk gets into some bad sets, and how to control these things. Okay, so you see, so that's more or less what you're seeing in the end. Okay, so for now on we'll fix an n, that n will be this n here, and also let's say greater or equal to 1, and I will not fix an integer a, I will fix some a, but a can be, I will fix some integer a, yes. I'll fix some integer a, and I also fix some c in z, 3n z, such that 3 does not divide c. Okay. So we have this this function here, this character, if you wish. So let me define key of x should be the character e to minus 2 pi I c x mod 3n divided by 3 to the n. Okay, so this stuff here inside is just can be written in, well, if we call arrays here, if we call what's the definition of Syracuse. So this stuff here inside is just key of f of geom. Okay? So one thing you can note is that key is multiplicative. Okay? So what we want to do really is to do key, as I mentioned, of fn of geom to the n. That's what we want to do. So let me just recall what geom is. So, let me just recall what fn is. So fn of a vector, let's say a vector, and instead of it, I will now put in opposite direction. So it should be f of a vector. So, but I will write the vector with decreasing indexes. So put an minus 1, a1. So this thing is um, 2 to the minus a1 plus 3, 2 to the minus a1, 2 plus dot dot dot. Yeah, if you put it in a different order, you see that it's a slightly different function than previously defined, but if you just switch the order of the indexes, you get exactly this. A1n. So that's the function. And again, recall that I'm using the notation, whenever I have a vector or a sequence, v1, v2, dot dot dot, I'm using the notation vi, comma j, should be the sum of VL from L from I to J. Okay. So that's our function, okay. What's geom here? Geom is just a vector where you have each entry is copies, so identically IID copies of geom2. So I could say that so now we fix an minus 1, a1 to be random variables equal to the geom 2 to the n. So each one, so you have just a sequence of IID copies of geom2. And geom2 is just a geometrical distribution over the positive integers. It just gives probability 1 over 2 to the n to the integer n. I shouldn't use n anymore. So n is fixed, so I should always use another variable if I want to use other things. So it gives probability 1 over 2 to the I to the integer I. Okay. So now let me define a new variable, which is Pascal. And Pascal will be just the sum of two geoms, but this sum is IID, which means I'm summating two independent copies of geom2. And if you do the calculation, again, you will have to use a product space. Pascal equals L, that would be exactly L minus 1 over 2 to the L. Okay. So it gives probability 0 to the integer 1. So Pascal really starts from the integer 2. Okay. So Pascal is Z plus valued random variable. Okay. Okay. So what I want to do is, so this thing here, this guy here, is exactly what I want to put, what I want to compute the expectation. But this thing here, this f is just a sum, and key is multiplicative, so this would be a big product of terms. And what I want to do is to group 2 by 2 terms here, so as to make this Pascal variable show up. Okay, so let me erase the other board. Okay, so yes. So what I want to compute right now is, as I told you, I want to compute 2 to the minus a1 plus 3 to the minus a12 plus dot 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 of 3n minus 1 to the minus a1n. That's what I want to compute. And then what you do some calculations here, and you realize that this is, again, I can split. First you get 2 by 2 terms, and when you get 2 by 2 terms, then you use that this is the key of a sum is the product of the keys. And then you split to a product. So for now, and let me assume for the moment that n is even. So let's assume for the moment that n is even. So if you do this, what you get in the end is the following. You get that this is the product from j equals 1 to n over 2 of key of 3 to the 2j minus 2, yes, 2 minus a1 2j and 2 to the a 2j plus 3 equals q. Okay. That's what you get. So I'm assuming n is even. Okay. But then what you do is the following. If you define b to be bj to be a2j plus a2j minus 1, in particular b1j equals a1 2j. So I can replace this guy here by b1j but these guys, bj, will be Pascal random variables because it's the sum of two independent copies of geom2. But I still have a to j, the final variable here. So if I want to replace everything by in terms of the Pascal variables, you can do it. So you have to, so basically what you do is you can put a copy of geom here and condition the expectation to the final bj to be a to j minus 1 and a copy of geom. So if you do that, and then I will put this as an arrow here as a problem, realize that this is true. It's not hard to realize that this is true, that this will be the expectation. So again, I will, so I want to put everything in terms of the Pascal variable, and I want to apply this trick here to do expectation of an expectation. So this would be the expectation of the product from j equals 1 to n over 2 of certain functions f of 3 to the 2. So note that bj is Pascal, and the b1s up to bn over 2 are IID. Okay. So this is bj, where f is the function. So f of xm is another expectation of key of x of 2 to the g1 plus 3 condition to g1 plus g2 being m. Where in here, in here g1 and g2 are IID independent copies of geometry. Yeah, because the thing is, well, this guy is independent of A2J, is independent of B1, B2 up to BJ minus 1, but it's not independent of BJ. So what you can do is you can just condition to the probability that Bj equals the sum. So this M should be the Bj here, if you see. So Bj is just the sum of two independent random variables, and you have to compute this guy here. So if you put x here, you will see you get exactly this, and g1 was standing here for this a2j, and then m here is standing for bj. So this would be a2j minus 1 equals bj. Okay, so that's how you see that the thing, everything is working. So you can either do it in a soft way, or you can even like open the both probabilities and open all the calculations and see they match. Okay, so you can realize that this is true. Okay. Okay, so what you see immediately is that f is the expectation of a character, so it has to be less or equal than 1. Okay, so if I were to do this with n to be odd, what I will get is I will get an extra term here in this calculation, and therefore I will get an extra term here in this calculation. But that extra term again will be f of something, which will be less or equal than 1. So if n was odd, similar calculations could be done. Okay, and we would get the following bound. We would get that the expectation of key of, so I want to do expectation of key of geom of etc. Fn of g1 to, so yes. So I will let me define define now. Maybe that will be better. So let me define left hand side, okay, to be exactly the expectation what we want to compute, which is key of that thing, Fn of geom 2 to the n, close. Okay, so that will be the left hand side. So we conclude that the left hand side, well, if n was even, since the left hand side equals this, we could definitely bound this by the expectation of the product of j equals n over 2 of the moduli of the f's. Okay, and if n was odd, there would be an extra term, which would be f of something, but again, that would be less or equal than 1, so we could just drop it and bound for by the same quantity. The only difference is that I have to summate up to the integer part of n over 2, so instead of doing this, let me summate n from this thing, where I define n over 2 to be the set 1, 2, up to the integer part of n over 2. Okay. So that's what we have. Great. So now what I need to do is to bound the moduli of f, or that is to bound these expectations here. Okay. So let me erase the other part. So all the calculations we'll be doing now is to finally to get into a point where everything looks like a random walk in the lattice Z2. Okay, so probably Tao knew what he wanted to do, and then we just step by step made the problem, the necessary adjustments to frame the problem in this random type walk situation. Okay. Okay, so the question is now, does a bound like this holds? Okay, so for this, let me now define. So let key of 3 to the 2j minus 2 to the 1 minus L of theta. So this will be an exponential of something. So it will be e to the minus 2 pi I some number, which I will define as. And that number should be a number, that would be an integer divided by 3 to the n. So that could be a certain number. Then you could always take the fractional part of it, but instead we would take the sine fractional part. So theta of JL would be the sine fractional part of whatever it was in there before. So there was a C 3 to the j minus 2. Oh, we had a mod 3 to the n, but since this is an integer, I can put on the outside anyway, because I'm taking the fraction apart. Where this function here is the sign fraction apart, which is defined as to be is defined as the guy in z. So you put an x in there. So you just translate x by all the integers, and you take the one in the interval. Let's see. Minus a half. Okay, that's the definition. Okay, that's a sign fraction apart. So some observations about it. For instance, if you do this, x, and you take the fraction apart, it's exactly as the taking the fraction apart of k. You first take the fractional part of x and multiply by k, and then you take the sign fractional part again. That's a trivial thing to show. Or another way of saying is that these are equivalent mod 1. Of course, if you have two numbers which are equal mod 1, they have the same fractional sign fractional part. Okay, so problem is some properties that we're going to need. This is actually an easy problem about this function theta, which is the following: theta of j plus 1 of L is congruent to 3 squared theta of JL mod 1, and then theta of L minus 1 is congruent to 2 theta L mod 1, and we also have an inequality, an identity we're going to need, which can be deduced from these two. So in particular, we will do an argument, a proof that we want that this equivalences mod 1 were actual identities, okay? This number here, which is the number between the minus a half and a half, equals this other number here, okay? Not mod 1, but an actual identity. But that can be done if, in particular, if this guy here, theta JL, in moduli is less or equal than some epsilon, and epsilon is sufficiently small. So for instance, let's say 1 over, it should be less than a half, I suppose, let's say less. Supposed to be less than a half, but you have a 9 multiplying here, so maybe less than 1 over 18 should be not sufficient for epsilon, for instance. So if this holds true, so epsilon is small, sufficiently small, then this thing here is actually a number a minus a half, and therefore it has to be identical to this. So then this is actually 3 squared theta JL, and so on. All the identities are actually, all the equivalences are actual identities. Okay. So this sort of thing we'll be using all the time in the following arguments. So why are we defining this theta? Well, because, we're going to evaluate the 2 to the j minus 2, which is in here, and also a minus beta. But beta is a distribution of the integers, and this is always like greater or equal than 1. So it's going to be a 1 minus L for some L. So that's why we define this this data function like this. Okay. So now we'll let gamma be this set, that plus. Okay. So that will be integers from 1 to n over 2, and these are all positive integers. So 1, 2, 3, etc. Okay, so, and then we will say that some JL in gamma is black if beta of JL in moduli is less than or equal to epsilon, otherwise we say JL is white. Yeah, maybe the best situation would be something like pink and blue, but anyway, it's black and white. Maybe that's not a good choice of names. Anyway, and epsilon here will be just some small, and throughout the whole lecture will be some small numerical constant. So we'll make epsilon smaller and smaller throughout the whole proof, and in the end you will say, well, if every epsilon was sufficiently small, let's say less than 1 over 1 billion, then all the arguments would work and the proof is right. So we fix epsilon equals 1 over 1 billion and everything works. Okay. So it will be a fixed but a sufficiently small numerical constant to be decided in the end, which will never be decided anyway. Okay, so another problem. So I'm giving the easy part for you to do as a problem, and I'm taking care of the hard part. So problem of show that so exactly what I want to do here. So if I put a J and L, and here I put the 3, so why 3? And the justification will come later, but basically is because well, Bj is a copy of Pascal, and Pascal has weight 0 for 1. It only starts with 2. Okay, but if Bj is 2, and then if all the Bj's here are 2, then you know exactly what the probability is, because there is only one. If the sum, if you have each one equals 2, then you know exactly what it's going to be. The only room left for uncertainty will be when Bj is 3 or higher. So that's why you're using 3. So that's the heuristic, for now, heuristic thing for 3. So this is e to the minus epsilon cube. Again, if epsilon is sufficiently small. If JL, and then, okay, so black, and we define the set of black points as B and the set of white points as W. So if this is white, that's the bound we get, okay? So in some sense, the black are the bad ones and the white are the good ones. So yeah, that's not a good choice of names. Okay. So a hint for this problem is that first of all you can compute what this f of x m is. It's not a difficult computation. It's m minus 1. So use that. So I will use that for m equals 3, for instance, which would be a very simple thing. To deduce that moduli of fx3 equals cosine of pi theta jl if x equals that guy there, 3 to the 2j minus 2 to the minus l. Okay, and since jl is white, it means that theta of jl is greater than epsilon. So this is away from the origin, and you can deduce this bound. Okay, let me erase this part. Okay, so in particular, the left-hand side we want to bound is less or equal. Well, we know that it is less or equal than the expectation of j n over 2 of certain functions, moduli of 3 to the 2j minus 2, 2 to the minus b1j, and then we have bj here. That was the expectation, that's what we did. The left-hand side is the original thing we want to bound. But then what you can do is that, well, since all these guys are less, all these f's is less or equal than 1, I can just restrict myself into the set. If you consider possible values, if you consider the values of b1j to be equal to l, you can restrict yourself exactly when you have a j and l in a white set. So if you do that, you realize that this is less or equal than the expectation of e to the minus epsilon cubed, and then the cardinality of a certain random set. And what this random set is just the j, exactly what it said, the j in n over 2, such that bj is 3. So what I'm saying is that once you consider that b1j is L, such that JL, so the idea here is to consider that b1j equals L, JL is white, and bj is 3. That way I will get exactly into this problem, and I can bound by e to the minus epsilon cubed, and the rest I can just bound by 1 because f has moduli less or equal than 1. So then I get here a random set, which is this guy here, and this is j b1j in white. Okay. So now if I think about it, really looks like a random walk. You have this lattice, so maybe we can draw something here. You have this lattice 1 n over 2 here, so this will be the j, and that will be the L. Okay, and you have some white and black points. It turns out that the black points will look like triangle, so this will be black. And this is going to be, if you look for the vector j b1j, this vector j b1j here, So you have coordinate j here at some point. And you were walking, you doing something like this, if you consider these vectors here. And you want to take those ones which are in this set W. So in a way, the black set, I can't deal with that. I just exclude the set, don't bother by it. Just bound the f by 1 in these guys. And the white set, which is somewhat better, I can do something like this. And I have this walk, and I'm trying to see what are these vectors, how many of these vectors hit the white set, okay? So in some sense, you're having a random walk here. But we will transform this into a kind of renewal process in a moment. Okay. So one thing, so the observation, and we can view this set here as a kind of a random walk, or as a kind of a renewal process. Okay, so you get a new bj, so you get a new bj, and you add to the sum, and you see if this vector hits the white. Okay. And at this moment, I can, well, white is already inside this box here, so I can actually think in other terms. I can just think that I have an infinitely many independent copies of Pascal, which are the BJs. I have infinitely many, and I'm just doing this. I can put greater or equal than 1, because being in the set W already restricts J to be less or equal than n over 2. Okay, so I can do that. And I can think now that I have infinitely many BJs. So I can think I have many B1, B2, B3, independent and identically distributed copies of Pascal, sorry. Okay. So now let me define another random variable. Let me define, so let j be the first integer such that, let's say, j equals, first integer such that bj equals 3. Okay, so you have the b's, etc., and you, as soon as you get to 3, you define this guy j here. So basically, you are in this product probability space, and you take a point there, and you then evaluate these bj variables, and as soon as you hit a 3, you assign this value j to this random variable j. Okay, so this is well defined in the product space. So j is well defined in the product space because the probability that b1 is 3 is you can compute is 1/4. Because it will be 2/8, which is 1/4. So the probability that bj is not, so the probability that b1 is not 3 and b2 is not 3 and and bm, let's say, is not 3. This is just 3/4 to the m, which converts into 0 as m goes to infinity. Therefore, in the product space, J is defined almost everywhere. Okay, so it's a well-defined probability, random variable. Okay. Okay, and it turns out that actually J is just another kind of geometrical distribution. So it's distributed exactly as geom 4, where in general we define, let's see, geom mu as a random variable, taking values in z plus valued random variable, such that the probability of geom mu being L is just mu minus 1 over mu, L minus 1 divided 1 over mu. So probability of geom 4 equals L is just 3 over 4 to the L minus 1, 1 over 4. Okay. So why J equals geom L? It's actually a nice, so probability of J equals L is exactly the probability of B1 not being 3 up to BL minus 1 not being 3, this be N, and BL being 3. But these are independent random variables, so it would be just a product of these probabilities times this, and this would be exactly that. Okay, so J equals geom, okay? It has the same distribution as geom 4. Okay, and now I will define a new random variable. Which I will call hold, which will be just J and B1J. So J, and it will summate up to the value given by this random variable J, the random variables BJ's. Okay, so that would be my new random variable. J, so let me erase the other side. So this is what's called a random shift. So problem. So let V1, V2, etc. Be IID copies of hold. Okay, so I have copies of hold and these variables V. So now these are Z2 valued. Well, actually, yes, J, hold can be anything up to, so this is, so hold is, so this can be anything positive, so Z plus cross Z plus valued. Okay, so it's something in this quadrant. Okay. All right. So the claim is show that this set, which is the set I'm considering here, which is the set JB1J for assuming that bj assuming that bj equals 3. Okay, so this will be a set. This will be a random set because you have this random probability, random variables here, and this set has the same distribution as the set v1, v12, v13, and so on, where I'm extending the summation notation to vectors now. So I have now a vector, and v1j is just the summation of vij is just vi plus 1 plus up to vj. So now these are vectors. I've extended the summation notation to the vectors. Okay. And what I mean by this is that the probability of a certain, let's say, JL belonging to the first set equals the probability of GL belonging to the second set. Okay, for any JL. So this is a bit more boring to do, but you can kind of realize, and the way you can kind of realize that is, maybe a hint, is that, well, if you have B1, and then at some point you get BI1, and that guy is 3, and then at some other point you get BI2, and that guy is 3, and so on. So you can think of, well, up to this point I will get the J, capital J equals I1 here. So so this guy here would be a, so this guy here would be a J V1, sorry, it would be a J B1J up to this point. And then if you start from here to that guy, you will get another one which is some maybe J1 here, J1. And you get another one which will be J2, B1, J2. Okay. But these guys have to be, so when you add them, you would get something like J1 plus J2 and B1 of, so you want to put J1 plus J2 here, and you can't because you're assuming that these two are independent if these are copies of hold. So you can, so you put J1 plus J2 here. Okay. So that's the way you understand that this set has the same distribution as that one. So that's the hint. Okay. And that's why this is called a random shift, because it is when you have these BIs here, whenever you get a 3, then you restart the process from there and you shift to the next 3, and then restart there and you shift to the next 3, and etc. So that's why it's called a random shift. Okay. Okay. So now we have this renewal process. Which is this V1 and then V1, 2, and then V1, 3, and etc. These all will be vectors. And then you want to see what happens when they hit a white. So in particular, we conclude that the left-hand side is less or equal than this, but this set here has the same, well, this set has the same distribution as this. So when it could compute, so that when I intersect with the white points, therefore the intersection of this set with the white points has the same distribution of the intersection of this set with the white points. And that would be exactly this thing here. So that would be the expectation of yes, so I can maybe it's written here someplace. This would be just the product. This would be just the product from k greater or equal than 1 of the expectation epsilon cubed. The characteristics of the set W apply in the vector 1k. Yeah, it was exactly, because this is once you replace by just the condition that V, I'm counting the J such that V1J belongs to W. Well, this is exactly this. I'm taking the product of all the things, and whenever it belongs to W, I put 1. So when I take the product, I will take the sum. So this is exactly this thing when I replace this set here by the cardinality of this guy, restricting it to belonging to W. Okay. Okay. So now I have to compute this thing. Okay. Yes, so maybe I can. Yes. So okay. So before I move on, so I mentioned that the black part. So okay. So now we have this renewal process, and we have these V's, guys. Now these things will be the V's. Okay. So you have this random walk, which can be seen as a renewal process. And you want to avoid the black sets. And I said that the black parts were like triangles. So I want to show that this exact statement. So I want to show that the black parts act like triangles. But I will leave that to the end of the class. Let me show now, let me continue with this trend here, and let me exploit this thing now. Okay. Okay, so I want now to reduce. So the question now is this something like this holds? Okay. So recall that the set, there is no n here, but the set W depends on n because it lives on this thing here. Okay. Okay. So what can we do now? So all these guys here are independent copies of hold, and hold is just a geom 4, and in here I have a sum of copies of Pascal, independent copies of Pascal. Okay, so that's what hold is. Okay, so I want to say that this thing, so we apply that iteration of the expectation trick again. So that will be Q of hold. So in some way I'm fixing one of the variables. And what Q would be, so Q of JL would be the expectation of the product of k greater or equal than 0 e to the minus epsilon cube 1W of JL plus V1K. Yes. Where whenever I put 1, 0, that means that the sum is 0. Okay. If there is no terms to sum, then the sum is 0. So what I'm doing here is that, well, I start from 1, so definitely I have a V1, okay, and a V1 in all these sums here, and the V1 is just a copy of hold. So I will fix that variable, so that will be JL equals to JL, and I will compute the expectation of the rest, which will have this form, but summation from 0, because the first term shouldn't be there, okay. And then I would just then replace this JL by hold. Okay, so that was just that trick again of iterated expectation. and an observation here is that we have this recursion formula, which is that if I pull this JL out, if I remove the first term here, I have an expectation of something, which is a constant, so I can just put this thing out. This is 1W of JL. Okay. Yes, just 1W of JL. And then we have this product for k greater than or equal than 0. Okay. Yes, but all these guys, so for k greater than or equal than 1, because I removed the term 0. So all these guys already start with one guy in here. Okay, so I could say that this is just the expectation of Q, because Q is like this, Q of G L, because all these guys would have, if I start from k equals 1, this product, all these guys would already have a copy of hold here, so I could just write JL plus hold and then put the other sums. And the other sums will now have to start from 0. So then we have this recursive formula. Okay? I'll be using that later. Not now. Okay, so now what we're going to do is I'll state the following problem. This is not so hard to do. You can show that hold has exponential tail. That is the probability that hold is greater or equal than lambda is decays exponentially with some small constant c, and that's more or less trivial. And that if you look for its covariant matrix is, so the covariant matrix of hold is positive, definite. Another way to check this is that hold is not actually a distribution that is only living in some coset of some proper subgroup of Z2. That will be equivalent to that. That's what Tao actually does, but you can just compute that and see that's positive definite. And has mean 4, 6. Okay, so therefore, in particular, it satisfies the conditions of the Chernoff type bound that I wrote, that I proved, which works for a general probability measure. So in particular, if you use that Chernoff type bound, which I think is lemma 22, in his I don't know what the number here, I think it's lemma 22, I don't know. So we can show the probability of V1k. So these are copies of hold, dependent copies of hold. This would lose to k minus 1 j gk c g jl minus k 4 6, where c is some small constant. Again, the same thing. C will always be some sufficiently small constant, and here we have that it decays exponentially far away from its average, yes. In particular here, if you put just k equals 1, which will be just the probability of whole being equal to something, which would be bounded by something like this, you would get you would get that here, for instance, and this is something we will use later. For instance, you can conclude the probability of hold equals JL. You can also conclude from this bound is, suppose that J and L are positive, for instance. That's where you can conclude. You can conclude from this or even from that. Okay. So lemma and I call this lemma 32. The thing 31 is yet to be will prove in the end, so I kind of reverse the order of my notes. Again, this is not hard to prove, it's just those kind of computations. So for S in Z plus, I will let R, which will be something which depends on S. So that will be a random variable R, to be the first K such that V1K is greater than S. Okay, so it will depend on S, but sometimes I will not put the subscript S. Okay. Oh, not V1K, the second coordinate of the OK, because V is a vector. So the second coordinate of V1K is just B. Is this B1 of so V1K, so if I write Vj equals let's say J and B1 JJ, yeah, he's writing here LK, so maybe such that if, maybe that's the best situation. If you write Vj equals JJ LJ, okay, so that would be B1 J sub J. Maybe I shouldn't use J. Let's use I. Such that if this is true, then so we would defer such that L1K, which will be the second coordinate of V1K, is greater than S. Okay. Okay. Because that's the variable R. So if I write these copies of hold like this, so recall, just to be completely clear, this guy should be B1JI. But I'm writing them as Li. Okay, so V1K would have second coordinate as L1K, and I'm taking the first K such that this holds true. Okay. Then probability of V1R, if I use this R as a stopping time, this loses to e to the minus CL minus S over root S GS CJ minus S over 4. No, it's actually S. I guess if you put S or S plus 1 doesn't make any difference, it's just to be S. Okay, so imagine that S is greater than 1, so there's no problem. And this is true if L is greater than S. Of course, if V1R, the second coordinate, which will be the L, is greater than S. So if I compute the probability of this being equal to this, better that L is greater than S. Okay, so let me prove that. I will only sketch the proof because there is nothing like too complicated with it. And basically, what this is saying is that V1R from a fixed S, V1R basically, so this is decaying exponentially if J is much bigger than S over 4 or L is much bigger than S. So so basically, heuristically, this is saying that V1R is basically the uniform distribution over the JLs such that J is S over 4 plus O over root S, and S is less or equal than S plus O1. Okay. But this has to be bounded, and also this has to be bounded in terms of this thing here. Yeah, in terms of this, because remember they have to take the square and then divide by S, so this, if you put root S, then all these things will be bounded. So basically, this inequality is saying that heuristically V1R is basically uniformly distributed in this set. Okay. So let me prove that. Oh, in my notes, this is with another name. This is with capitals. So let me put capitals here. Okay, sorry. So we know that VK is JK LK. Great. JK is just a copy of G on 4. And LK is basically a sum is just Pascal plus Pascal, and this is an IID sum of copies of Pascal. Okay, that's what we know, because and how many terms we have exactly JK, have exact JK terms. Yes. Yes. Okay, so that's what we know. So let me erase the other side. So then the probability of V1R equals 1L, JL will be, so what we know is that if I choose R to be the first, so L1R minus 1 is less or equal the first, which is greater than S, which is greater than L1R. Okay. But then in particular, but since L1R is L1R minus 1 plus LR, I can say that LR is greater or equal than, well, I can, oh no, what I want to do is not that. What I want to do is rewrite this guy here as L1R minus LR. So therefore I would know that LR is actually greater than L1R minus S. So LR is greater or equal than L1R minus S. Okay, so that's okay. So if L1R equals L, which is exactly if I do this thing, then I know that LR is greater or equal than L minus S. So I can bound this thing by just the sum over all the k's greater or equal than 1 of the probability that V1k equals JL and LK is greater or equal than L minus S. Okay, because it has to be a k where J or V1k is JL, and I know that if in the situation I want to compute, I want LR is greater than this. If this is L, then LR is greater than L minus S. I have L minus S here. Okay, so I can then write this as a triple sum. So I can, well, this is a sum, so I can say that the sum up to k minus 1 is something. Of course, so this guy has to be less or equal than L because I'm putting L minus LK, this has to be positive. And VK has to be, and it has to be greater or equal than L minus S because I know that the very last one has to be greater, LK has to be greater than L minus S. So that's it, because I'll say that this equals to LK. Okay, so LK, which is LK, which is the second coordinate of VK, is little LK, and that guy has to be greater or equal to L minus S. So I have to impose this condition here. Okay. Now we know that the probability of hold equals something decays exponentially. And this guy is just a copy of hold, okay, independent from the rest. So I could just put hold here if I want. So I can then remove that term and put just k greater or equal than 1, jk less or equal than j, L greater or equal than L, k greater or equal than L minus S. And then I do e to the minus c, jk press lk, and then the probability of v1 k minus 1 equals jk KL minus LK. Okay, so I can then write LK and make a change of variables. LK should be L minus S plus an LK prime, and then LK prime should be at most S. So, and but greater or equal than 0, so you could put 0 here, and most S prime. And then L minus LK is S minus LK prime. Okay, so now we have this. Well, J is the first coordinate, and J has to be positive anyway. So I want J. J greater equal than 1, of course. And these guys have to be greater equal than 1, so this is greater equal than 1, of course, because they're dealing with distributions over the positive integers. Okay, great, that's what we have. And now the idea is to use this thing here, is to use the problem. This thing here is bounded by k minus 1, gk minus 1, c of g minus jk, s minus l k prime minus k minus 1, 4, 6. Yes, close here. So this is another explanation of Gaussian. So just replace this thing in here, and then you have to evaluate the summation, and we'll let for you guys to finish. But then you evaluate the sum. When you evaluate the sum, sum to finish the proof. Okay, so I'll leave this as a problem. So you can see lots of problems, but they are not hard. They are just the easy pieces of this big puzzle. And if you have problems solving any of these problems I put here, just send me an email and I can help you with that. Okay. So that would finish the lemma. So it's nothing like a big idea. It's just a kind of observation you can do. So you have these kind of things. Okay. Now we'll define QM. So now we'll make really a reduction that we'll be working on to prove. So let QM be the soup over JL over gamma. So recall that gamma is just a lattice from 1 to n over 2, and then from 0 to infinity for L. Okay. So this gamma here is n2 cross z plus. Okay. So of this thing's n over 2. Integer part minus j, we'll put the plus 1 here just to avoid this to be 0, and then qjl. Okay. So recall that what I wanted to compute now was the final form of the left hand side was bounded by expectation of q of hold. Okay. So this, in a way, I'm trying to bound this expectation. Okay. Okay. Then we will show the following, which I will call star. We'll show that there is some CA and epsilon, which depend on epsilon to be sufficiently small, but then it will fix later, so it won't depend on epsilon. Positive, so that if CA epsilon is less or equal than m, it's less or equal than n over 2, then from some point on, then this quantity starts to decrease, okay? So kind of an energy, and the energy starts to decrease from some point on. Okay? So we will show that. So that's what we were working on. We're working on showing this. Okay, let's see how this finishes the proof of the proposition. Let me erase this part. So the lemma I presented here was just preparing for the following parts. We'll actually not use this lemma now. So we knew that the left-hand side that we wanted to bound was actually bounded by expectation of Q will hold. Okay, that's what we had. But if this is true, then that in particular implies that, well, if I take the supremum over the set, well, it's actually just, the supremum will be just Q at this number, CA epsilon. The supremum of Q over the set would just be evaluating Q at this point. And then before would be something, we can just take the supremum, all of them, and then it would just depend on A. So that implies that the max of 1 less or equal than m less or equal than n over 2 of Q is basically just depending on A and epsilon, but it's just bounded. Okay. Okay. So if this is bounded, it means that the quantities here are bounded in terms of that. So we know that Q of hold is something A epsilon of so Q of hold, it will be bounded by this thing inverted. So it would be N2 minus J plus 1. Remember that hold was J and then something else. And this J should be this J here, the first coordinate. So this capital J, which is the stopping time, which is the first guy that B was equal to 3. And this was geom 4. Yes. Would be just the expectation by this. But so this is geom 4. But then we can bound this thing here just by some constant depending on A. Is it something easy to show it? Maybe the multiplicative constant from this to this is like 2 to the A, something like that. This would be just n to the minus A and then J to the A. Okay. So I'm saying I can bound it. You can bound stuff like I minus J. You can bound by you can bound by something like J over I. Okay, that's the claim. So this J would be this capital J here, and this I would be the N. Okay, so I raise both sides to the power A, you'll get a bound like this. Okay, that's what I'm claiming. It's easy to see. Okay, so then I'll have to take the expectation of this. But J has J is GM4, and therefore the expectation of J to the A is bounded by a constant dependent on A of 1, because J has exponential tail, or either you could just go ahead and compute this, would be just a sum of some thing that grows polynomially times something that decays exponentially. So therefore, will be summable and will be finite. Okay, so this thing is just bounded by some other thing that depends on A, and then the expectation can come out, and then the end comes out. Okay, which is what we wanted to show this whole time. So this would finish. So this would finish proposition 28 or 29. That's the proposition we want to show now. Yeah, the one about the expectation of the character function. Okay, so that would finish. So we will work towards proving this thing. Okay, so and we need a bunch of auxiliary results. So I already did one before I mentioned this, which was the one about this thing here, the variables v1r. And then we need another one, and this other one, which is, so what Tao does is say that the proof has two parts. One is deterministic and one is probabilistic. Okay, and the deterministic part is about the structure of the black sets. So remember that the function q here had a weird expression. It was an expectation of a certain product, and this product involved the characteristic function of the white sets evaluated in these variables v1j. Okay, so we still have to figure out how these white and black sets behave. And so the deterministic part would be about the structure of the set we want to avoid, which is the black set. Okay, so let me state here the proposition. Okay. Okay. So let me first make a definition. And the definition is the following. Yes. The definition is that we define a triangle. So I have this set which I call lambda. So okay. So we had this set lambda. Okay, and we had black points and white points in there. So black. So we call it black was if theta JL was less or equal than epsilon, and white was if theta JL was greater or equal than epsilon. Now epsilon is some sufficiently small quantity. So let me define these triangles here. So triangle J naught, L naught, S naught. If I give you a center and a radii, this would be just JL in gamma, such that J is greater or equal to A naught, L is less or equal than L naught, and 3 to the 2 to the J minus J naught, 2 L naught minus L is less or equal than E to the S naught. Okay. Okay, so this thing here on this side is really a linear condition, because if you just take logs on both sides, it's just saying that j minus j naught log 9, so this is equivalent to saying that j minus j naught log 9 plus L naught minus L log 2 is less or equal than S naught. So this is really a linear condition. So okay. So this is something like this. So this is a triangle like this. This is J naught L naught. This size here is S naught over log 2, and this side here is S naught over log 9. Okay, and this is the triangle, and this is the left up corner. Okay, so problem, let J naught L naught be black, and so therefore it's less or equal than epsilon, so I can write a J theta J naught L naught moduli as epsilon e to the minus S naught from some for some S naught greater or equal than 0. Okay, then the triangle J naught L naught S naught is all black. Okay, and basically the hint here is that you have to use the theta of JL is congruent to, whenever you have a JL in this triangle, is congruent to 3 to J minus J naught 2 to the L naught minus L theta of J naught L naught. Okay, once you use this, it's congruent to that mod 1. This was part of the problem, the properties about the function theta. So if you use that, you can easily show that whenever you have a triangle like this, these are all black. So the point is that the black dots are just a union of a bunch of black triangles. Okay. Let me raise that board and write the lemma we want to show. So this is not hard to figure out because, well, since S can be anything, a black dot is to be considered as a black triangle. So of course that the black set is a union of black dots, and therefore it's a union of triangles. That's what I was saying. What I'm saying is that if you consider a collection of maximal triangles, with triangles which cannot be extended, then you have some special properties about them. Okay. Okay, so lemma 31. Which in my notes was before that the other lemma I presented. So I can write the black set as a disjoint union of triangles. Okay, belonging to a certain triangle set. Moreover, such that is obvious. But this is not obvious. You can make that thing into, you can split the blacks in union of triangles in such a way such that the distance of any triangle in the family to the vertical line n over 2l, l greater or equal than 1. So the distance to this line is greater or equal than some small constant log of 1 over epsilon. So again, sufficiently small, that will be chosen later. And 2, distance, but numerical, yes. and the distance between two, such that for every delta and delta prime in t distinct, distinct would be with empty intersection. And the distance between any two of them is greater than. Okay. So the drawing should be something like, you have here L, you have here J, and this guy is n over 2, and you have a bunch of triangles here, and they are separated. So there is a tiny slit here of separation, and there is also a separation here, and this separation is about c log of 1 over epsilon. Okay. And in the distance here, we're using the L1 norm in this set of lattice points. Okay. You could use any other norm, but the L1 norm will be better for this situation. What else? Okay. Proof. So let's prove 1 first. So 1 is kind of easy almost. So let J1 L1 be a black set. We have to show that there is a separation from the vertical line here. So basically, I do know that theta of J1 L1 in moduli is less or equal than epsilon, but that is the same to say that, remember the definition of this guy, which was exactly taking the sign fractional part of this. So if we do mod 1, it means that this thing belongs to this interval mod 1. In particular, if you multiply by 3n plus 1 minus 2j to both sides, what you get is zeta xc to the 1 minus L mod 3 to the n divided by 3. And so that has to belong to minus epsilon 3 to the n plus 1 minus 2j. Since you're multiplying by integer on both sides, you still have this. But recall that c is not divisible by 3, and this guy here can never be congruent to 0 mod 3 to the n. Therefore, this integer here in the numerator is not divisible by 3. So therefore, this thing here is congruent to 1/3 or 2/3 mod 1. Okay? So worst case scenario is that it is equal to 1/3. So we conclude that 1/3 lies in its interval, so epsilon 3 to n plus 1 minus 2j is greater or equal than 1/3. It can never be bounded by this. So if you take log on both sides, you conclude that j is less or equal than n over 2 minus c log of 1 over epsilon for some c small by taking logs on both sides. Yeah. So that's done. That was easy. Let me go for the second one. So for the second one, so maybe I should make a bigger picture on this side here. So suppose you are in here. So suppose my J1 was something here. That was J1, L1. How can I get this corner here? What I do is I go up until I can go up more. So I hit a white point here. Then before I hit it, then I go left at most as far as I can. And then I can't do any more. So I hit a white point here. Okay, so this guy will be constructed in this way. So go up, choose something like J1 L0, and go left to J0 L0. So all this inside the black set. So I go up, then I can't go any more up, then I go left until I can't go left anymore. All this I'm walking inside the black set, so that J1 L0 L0 plus 1 and J0 minus 1 L0 are white, but so I'm going up, so J1 L and J L0 are black for L less or equal than, so I'm going up, so I'm going from L1 to L0, and I'm going left, so J0 less or equal to J less or equal to J1. Okay, so that's exactly the picture. I'm walking here inside the black set, and I'm going left. Okay, so let me erase this part. Okay, so now let's JL. So what we have to prove in here is the following. So I define a certain triangle. Okay. So now what I have to prove item 2 is I have to show that if I'm not in a triangle, so first I have to define what a triangle is. So theta J naught is definitely less than epsilon, so moduli is epsilon e to the minus s naught. And delta to be the delta of J naught, L naught, S naught. Okay, so that guy here is the triangle delta. Oh, I draw another triangle. This guy is the triangle delta. Okay, so let JL not in delta, and I want to show that if J naught is not in delta but is close to delta, but distance of JL to delta is less than epsilon, okay, then I want to show then I will show JL is white. Okay, so if it's not in a triangle but it's close to it, then it's white. And therefore, J1 and L1 has to be black. It has to be inside this triangle I just created, because if not, if it was here, for instance, then I could go up, this all would be black, and it will hit the point here, which is just about to enter the triangle, but it's white, about to enter the triangle, so that point should be white by this, because if it's close and not in the triangle, then it should be white, but it's black by construction, because I'm walking by construction, all this line here is black. So that would be impossible. So J1 and L1 have to be inside already. Okay? The same thing if J1 and L1 was here. So go up here, and then when I walk left, I will hit some guy in here. Okay, so that would show that J1 and L1 belongs to the triangle, and also that any other point which is not in the triangle but close to it has to be white. So in that way I build a triangle, and if I get any other black point which is not in this triangle, and I build this other triangle, the other triangle related to this other black point in the same way, I know that these two triangles have to be this distance apart. And I just keep doing this process until I fill B with a union of disjoint triangle, and they will satisfy property 2. And I know that any black point is far away from the vertical line like this, so property 1 will also be satisfied by this by this union. So okay, so all I need to show is this, that by what I just said, all I need to show is this. Okay. So then we will separate in cases. So maybe you should draw a picture of the cases here. So here, this region would be case 1, this would be case 2, and this would be case 3. Okay. So I'm assuming that I have a JL fixed, not in this triangle that I just built, but it's close to it. So I need to conclude that this is white. So case 1, suppose that I have a point here, so there is J greater or equal than J naught, L less or equal than L naught, and also 3 to the 2 to the J minus J naught, but then it doesn't satisfy this thing, so this is greater than E to the S naught, okay, which was the linear condition defined in the triangle. Okay, so that would be a point here in this region. Okay, but I know that it's close to the triangle, so I do know that the norm 1 of J to J0 and L to L0 is small, so I can say that this is less or equal than E to the S naught plus here plus O of C log of 1 over epsilon. Because I know that J minus J naught moduli, L minus L naught moduli is bounded by this. Yes, just because knowing that it's close to this triangle, I know that this relation is the same to say that this point is close to this line, which is the same to say that this relation here is close to being satisfied in the exponents, which is the same to say this. Okay. Okay. But then I know that theta JL is congruent to 3, 2 to the J minus JL, L naught minus L, theta J L J naught L naught. Okay, again by the properties I ask you to prove about J, I know that if I add 1 here, I have to multiply on the other side by J, and if I know to subtract 1 here, I have to multiply the other side by J. So therefore, I can go from a big J to a small j by multiplying by 3, and I can go to a small l to a big L by multiplying by 2. And okay, so these are congruent mod 1. Okay, but what is this? Well, this guy here, if I take the moduli of this guy and put it here, what I do have, I have something like e to log, well, sorry, I can just use this relation here, I can just bound this, replace this thing here by this, and this guy here is just epsilon, by definition, epsilon e to the power minus s naught. So the minus s naught cancels with this, and you just get e, and then we get epsilon of O of c log of 1 epsilon, and this is just epsilon 1 minus O of c. Okay, so if c is small, this is going to be small, going to be less than 1. So if epsilon is small, so if epsilon is small, I'm always assuming this is sufficiently small, and this O here is just a numerical constant, so it will be sufficiently small depending on the numerical constant. I know that this is less than a half, for instance. Okay, so this number is less than a half, this number is less than a half, so therefore they have to be equal, because they're congruent mod 1. Identity is true, and if identity is true, then we can take moduli, but the moduli of this guy, we just bounded, is less than epsilon 1 minus O of c. No, sorry. So, yes. Okay. Sorry. So this number equals this. Then I can just take the moduli, but then I know that this inequality is true. That this is greater than that. So if I just replace, I get that this is greater than e to s naught, and this guy is just e to minus s naught epsilon, so this is epsilon. So JL is white. Okay. So basically, and then we repeat this in case 2, the strategy is just, okay, we have some identity, which is mod 1, and by some inequalities I can make it a true identity, not mod 1 anymore, and then from this I can do some inequalities, and these inequalities will imply what I want to show. Okay, so that's the basic strategy. So case 1 was the easy one. Let's do for case 2. So we'll do case 2, and we'll leave case 3 for you guys to prove. Okay. So let me do case 2. So case 2, we have that j is greater or equal to j naught, again on this side, but now L is greater than L naught. So I have a point here. So this guy was L naught, and this guy here was J naught. Okay, so we have that. Great. So what's the idea? Well, we have this point here. So maybe we go to this part. I have a point here. The idea is to derive a contradiction from the fact that this guy here, it has to be white. That along the line, just above the line L equals L naught, so the line L equals L naught plus 1, there is a white guy here. This guy here is white, which is exactly this statement here. That this guy, J1 L0 plus 1, is white. Okay, so I want to get a contradiction from this fact. So we assume that this is black, and then we get a contradiction from the fact that there is a white guy there. Okay. So then we have the L naught, since the point has to be close to the triangle, we do have this.
it could be the case that j minus j naught log 9 minus s naught is actually negative. So I'm saying that this is bounded by a constant which in moduli is less than this, but this is bounded by a positive constant, this guy here. Well, but that's obvious because a negative thing is bounded by a positive thing, okay? Because this is positive, okay? So, so when you look to this, really imagine me multiplying by a numerical constant this whole thing here. So this inequality could be trivial if this is negative. Okay. So this basically is the case if I have a point here, then the closest point would be in this corner here, and so that inequality would make sense. But then if I put here, then the distance will be just going down, so that inequality here won't tell me anything. Okay. So we have what we have. We have the 2j1 L naught plus 1 is congruent to 3 to 2 j1 minus j naught. So again, I can always go down in j and I can always go up in L. So then I have yeah, j1 is bigger than j naught, so I can always do this. And I have also that theta j1 L naught is congruent to 3 to the same thing. Yeah, so let me write the same thing. And this is congruent to theta j1 L naught, everything mod 1. Okay? So first of all, this thing here, so if j is greater or equal than j1, that there is, the right side of this line, which I made to construct this triangle, so the point is here, then this guy here, I can bound by, I have j1 minus j naught, but it just replaced by j minus j naught, and j minus j naught loses to s naught plus o of something, and this guy is just epsilon e to the minus s naught. So if I do the calculations, I get just exactly the same way before. I just get this. So if epsilon is small, that means that this number is smaller than a half, for instance, smaller than a half. Therefore, these two here have to be actual identities. Okay, so this guy here is an actual identity if epsilon is small. So I can remove the mod 1 from this. Okay. Yeah, so this I can always go down. And now we have these two guys here. Yes, so the point is, if epsilon is small again, then these two guys here will also be an identity. So if epsilon is small, these two guys will be an identity, and if epsilon is small, these two guys here will be an identity. So let me erase the other part. Or maybe I should let this drawing here. this. Yeah, because, well, this is a small, so this number here is a number, yeah, if this guy is small, then these two will be identities, okay? So if this epsilon is sufficiently small, then I will have that these two actual identities, so I can replace these two guys like this, and I will have that then theta J1 L0 is actually equal to twice theta J1 L0 plus 1. Okay. But what is J1 L0? It's just this guy here, and this is the white guy. So this guy is white, and this is supposed to be black. But if this is black, this is less than epsilon. So this will be less than epsilon over 2, so that's impossible. It's a contradiction. Okay, so we conclude that J has to be less than J1. So the point has to be in some place here. Okay? So J0. Okay. So we have this range. Okay, so now the conclusion, yes. So that can be the case. So the guy has to be there. Okay, so now assume by contradiction, assume that by contradiction, that that JL is black. Okay, so I know this restriction already, okay, but let's assume that it is black. So the idea now is to show that, so we have this guy here which is black. So the idea now is to show by induction, so maybe we can draw a bigger thing here. So we have something like this, and my point is, this was my J1 line, this was my J1 line, and there is a white here, and my JL is some place here. So I want to show by induction that these two guys here are related, exactly in the same way, like this. So twice this guy up here equals the guy down, equals as identity, not in model 1. And I will show by induction that if this happens, then this happens. These two are also related. These two are also related. And then finally we'll get to this point here. And that will give me a contradiction because this guy is white. Okay, so that's the idea. And a similar technique can be applied for case 3, which I will leave as a problem. Okay, so we know that 2J L0 plus 1 is congruent to 2L L0 theta J L. Okay. Again, the J's here I can go down, and the L's I can go up. So I'm going up here. Okay. So again, these two guys, L minus L0, by this inequality here, and the fact that I'm assuming that JL is black, so this is almost epsilon in moduli, and then when I multiply by this, I get something like epsilon 1 minus, so this, again, this thing immodalized, let's say equal to epsilon 1 minus O of C. So therefore, these two have to be equal as identity. Not mod 1 anymore, but equal. Okay. So this guy here also has to satisfy the same bound. This is less than 1 minus OC, epsilon to 1 minus O of C. But this guy is congruent to theta J L naught. But since this guy is small, therefore this identity, this congruence has to be an identity. So this has to be equal. So we conclude that theta J L naught equals twice theta J L naught plus 1. And theta J L naught in moduli, since it's equal to that, which is equal to this, and this is this, I'll see. Okay. So what I conclude is that if I go down here, these two guys here are related by an identity, and I know how to bound this guy below here by something like that. Okay, so assume by induction, so assume inductively that yes, L naught equals twice theta J plus K L naught plus 1. So now I'm walking to that direction, and that theta J plus K L naught in moduli is less or equal than epsilon 1 minus O of C. Okay, so now I want to show this for K plus 1. Okay, so I'm increasing the J's and going in the direction of the J1. Okay. So we know that 2 theta J plus K plus 1 L naught plus 1 is congruent to 3 to J naught theta J naught plus K plus 1 L naught mod 1. Again, I can always go down here. Yes, I can go down. Yes, I can always go down here and go up and down. Let's forget. Okay. But since I'm in this line here, and I know that this line always have black, so this guy here is black. Because of course I'm assuming that J naught plus K is strictly less than J1. So I still didn't reach J1. So this guy is black. So this is less than epsilon, and I have J minus J naught, so I can use this bound again. So this whole thing here in moduli is less or equal than 1 minus O of C. Okay. Therefore, this thing is an identity, not mod 1 anymore. We can erase this. And therefore, this guy here has the same bound, but this guy here is congruent to theta J plus K plus 1 L naught. But again, this guy is modulized less than this, so therefore this is also an identity, and this guy satisfies the same conclusion. So we conclude that. So that's exactly the induction step. Okay, so as long as I get a black here, I can do this. So by induction, we conclude what? We conclude that this guy here have to be, so I will walk down this line and always get blacks, 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 and blacks, and etc. And this all came from the base case, and what the base case related was possible because I assumed that JL was black. Okay, so by induction I will conclude that theta of J1 L naught is equal to twice theta of J1 L naught plus 1 in particular. But this guy is black, therefore this guy cannot be white because they're equal, so it will be half of some black and half of a black is to black. Therefore, impossible. We get a contradiction. So JL was in fact white. Okay. So this finishes case 2, and then I will leave case 3. Case 3 as a problem. Okay. So let me erase this side. Okay, so now we just have to prove the inequality star that I stated, and actually stated it in a slightly incorrect way. And actually from Tao's paper, I couldn't actually realize the statement or understand what the inequality he wanted to prove. But I managed to prove, you can manage to prove something else that in any way implies the claim he wants. So I put as inequality, so I just stated before I proved this lemma what the inequality was, which I call a star, which is if I define these quantities Qm to be the sup of GL, that J is greater or equal to n over 2 minus m. And in here I put something which was 1 plus n2 minus j to the power a, and then kjl. But actually, just to follow exactly, I think in the end it won't matter, but just to follow exactly his notation, he put here actually his way of doing, yes, just max between this and 1. They're comparable, so that there's no problem. So that's the first modification I have to do in the star inequality that we want to show. And actually I stated it then for m greater or equal than some constant of a, and of course m less or equal than n over 2. So in this range we had that Qm is less or equal than Qm minus 1. Okay, so this is what we want to prove. But actually what we want to prove is that from this we deduced that if you have this, of course you deduce that Qm is bounded by some constant depending on a, and also an epsilon by 1 for m in this range. Because you can go all the way in this inequality up to get to Ca, so all these guys will be bounded by Q of Ca, and from 1 to Ca you just take the maxima, that will be a constant dependent on a only, so you then not on n, so you then bound this. So this is what we want to deduce. And from this we completed the last proposition, which proposition, I forgot the number. And the last proposition implied the whole result. Okay, so that's what we want to prove. And from his paper I could only show that, not this, but I could only show this one. That the max between some large quantity that says Ca tilde of this quantity with Qm is, that quantity is decreasing.
Okay? I can only show this. So let me erase this part here. It's weird. So this is CA, that's equaling M, that's equaling this. So this was the only thing I could show, but this implies the same thing, because either QM stays below C tilde A, which implies a result for M sufficiently large, or not. And if that is the case, then it definitely stays below the previous one, and then you can just iterate this inequality and say that this thing is bounded by QM here is bounded by the same quantity but with M replaced by CA, and then, well, this is a maxima, therefore QM is uniformly bounded. Okay, but this was the only thing I could show, which implies the result anyway. Okay, so now this is the thing we want to show, and then I will put a problem which would imply this. So problem, and in Tao's paper he just states that, well, this problem implies the decreasing property of the quantity QM, but it could only imply something like this. And this is definitely true, but the other one I couldn't manage to do. So use so the problem is that show that star is implied by the inequality which I will call star 2, which is QJL less or equal than M to the minus A, QM minus 1 for L greater or equal than 1, N over 2 greater or equal than J greater or equal than 1, and M set to be exactly equal to N over 2 minus J. Okay. So if you show this, then this implies star. Okay. So that's the problem. It's not a difficult calculation. It's just let's say a 5-line computation. Okay. So next. So now we want to show star 2, and what's the idea? Well, the idea is so let me recall you what QM is. So QJL, what it is just e to the minus epsilon cube, indicator of the white points times the expectation of Q of JL plus hold. So there is so this is the recursion formula we stated, and Q is actually defined, QJL is actually defined as the infinite product. But that from that infinite product, the expectation of the infinite product, which is not infinite, we will stop eventually. But then from there you can deduce a recursive relation. That's the recursive relation we had before. Okay, so so what we're going to show here is that we should change this. That, well, there are some cases you have to consider. So first case would be the case that, well, you already start in a white point. And that would be the easy case to show star 2. But you could also start in a black triangle. And if you start in a good region, then you can just iterate this formula just a few times, and then you will reach with high probability a white point. And if you reach with high probability a white point, we'll be able to prove this inequality again. and then you only need to iterate a few steps. And the hard part is when you are like deep inside a triangle, a black triangle, so you would need to iterate until you reach a white point. That would take some time, relatively speaking, but then that won't be enough, so you have to iterate some more times so that you get a bunch of white points, and then that will give you this inequality. So white points, you will see in a moment that white points is the easy case, it will give you this inequality almost instantly. And if you are in the upper part of a triangle, a black triangle, you just need to iterate some few more steps to get a good white point, and we'll get this back again. And if you're deep in the black triangle, then you have to iterate a bunch of times to get a bunch of white points, so that to compensate for being inside a pretty bad region. Okay, and that's the hard part. And this hard part is basically just it just open up all the computation. There isn't much of a new ideas. I have a bunch of new ideas. This paper is very technical but very nice, with a bunch of new ideas. I guess they are not that new for Tao maybe. But the final part is basically just grunging in, using all the lemmas we already did, and just open up the calculations and applying some inequalities in a clever way. And I will leave that as the final case. I will leave as a reading problem as well. Okay, so I will do this the first two cases. Okay, which already illustrate the idea behind this final step, which is by using this renewal process. Okay, so let me do case 1. So all we want to do is to show star 2. Okay, so that will solve everything. So let me do case 1. Well, case 1 is is the simple one, when you assume that you started in a good place. You started in a white point. Okay. So always recall that, well, M will be defined. M will always be this guy. Yes. So what we have here, we'll just have this thing here, okay? And then you have here, so you could just, of this thing here, this KJL plus hold is bounded by, just put this in the soup here, so you can plug in the quantity QM. But hold is a copy of, is a vector. The first entry is always greater or equal than 1. So if you add up j by 1, you are actually reducing m by 1, which implies that you can actually use this bound for k minus 1. So since j L, so recall that, let me just recall here. So recall this. So hold is the variable j, which is a copy of, we showed that genome 4. And then we have some sums here, which is b1j. And the b's are copies of the Pascal random variable. So since you have a sum here, so you have j plus j, and then j is, by definition, is n over 2 minus m, so I can do this. And j is always greater or equal than 1, so therefore this is greater or equal than m minus 1. Okay, so therefore when I bound this quantity q here, I can use m minus 1. So from this you get already that qj, oh, this is not good, let me change this. Maybe that one. Oh, that one's better. So the qjl will be less or equal, just using this bound here for m minus 1. You have here qm minus 1. It belongs to a white point, it's a white point, so this is just epsilon cubed, and then expectation of what? You just replace by that, so it will be the maxima of 1
maxima of 1, and n over 2 minus whatever is the j, but the new j is just little j plus capital J, which we know, so it will be n over 2 minus this, so we know it's just j minus n. So this would be, oh sorry, n minus j. So it will be n minus 2, yeah, n minus j, exactly, so n minus j. But this guy here to be n over 2 minus this, which is n minus j, okay? And raised to the power minus a. Yes. Yeah, that's what we have. And then we have a very nice inequality which I put as a problem, which is this one. That the maxima, and this works for any numbers, 1 n minus, let's say, little r minus 1 is less or equal than m minus 1. And then here is e to o of r log of m over m. So this is just a nice inequality that we'll be using. Okay, and that's exactly what we have here. So if you raise both sides to the power a and use this inequality, what you get is that this is less or equal than q to m minus 1, e to minus epsilon cube, expectation of e to o of a j log of m over m. Yes. Okay. So, but what happens now is that j here is a copy, as I said, of geom4. So it has exponential tail. So if m is sufficiently large, the multiplicative constant here will be very small. So basically what you're doing here, if you compute this expectation, this would be just will be roughly like summating 3/4 to the power L multiplied by e to some, let's say, alpha L, where alpha is very close to 0. So that thing will converge if alpha is very close to 0. And we converge to, and you have to multiply everything by 1/4, and then you will converge to something which is very close to 1. Okay, and it will be as close to 1 as you want if alpha is very close to 0. So you can show, and it's not hard, just open this calculation, you do it. You can show that you can bound this thing here by choosing m sufficiently large. You can bound this by something like e to epsilon cubed over 2. So this whole thing will be qm minus 1 e to epsilon minus epsilon cubed over 2. Oh, I forgot the m to the a from the inequality here. Yeah, there was a minus 1 here, which raised to the a is a minus m minus a. Okay, and well, but this thing is less than 1, then you just show the star 2. So that finishes it. Okay. So case 1 is easy. It's just like a 2 or 3 lines inequality. Once you know this inequality here, once you know this thing here. Okay, so let me erase that part. So now let's go to case 2. Case 2 is a bit more complicated, but not that much. So assume now that JL is not white, and therefore by the lemma we made, So therefore, by the lemma we did, it has to be in one of these triangles, black triangles. So it has to belong a certain triangle with corners J delta, L delta, and size S delta. Okay, and then we require a certain property, but L, the point JL is greater or equal, well, L has to be always less or equal than the L delta, but it's not too far away, so M over log squared of M. And why this quantity was exactly why, because of this. We would do an inequality like this, and it will show up something like log M over M here, and it will be dividing by this stuff here, so there will be a surplus of a log M that we'll be using, so that's why, so log squared of M. Okay, so what this part corresponds, so this is your triangle, so I'm assuming that I am in a triangle, JL, but I'm not too far away from the border here, so I'm in some region here. Okay, so that would imply that if I iterate just a few steps, I will get out of the triangle here, and I will get to a white point, which is a good point, which I can replicate something like that. Okay, that's the whole idea. White points are good. If you're not a white point, just iterate, and you have to control how many iterations you do. But once you control it, then you can use the easy part with the white points, and then come up with something. Okay. Okay, so now let me define S to be L delta minus L, which would be this gap here. So by the condition S is something greater or equal than 0, but less or equal than M over log squared of M. So let the variables Vk be Jk, Lk. So these V's are copies of hold, so this Lk should actually be a B1Jk, but I would just write as an Lk. So Lk is a B1Jk. Okay. What else? And now so S in lemma, I think it was lemma 32. I define a certain stopping time, which I call R, which depends on S, be the first, so that L1R is greater than S. Okay, so what is that? That's exactly the first moment, so I'm iterating, that's exactly the first moment that the height of this process gets above, this is the L delta height, above L delta. Why? Because, well, S is L delta minus L, so, okay, so this is the first time, so R here is the first time, so that if I add L, little l on both sides, so I cancel, so that means that if I start with JL and I iterate by adding hold variables, independent sums of the hold variables, which is this guy, so the second coordinate will be this guy's here, and then it will be the first time that I get to here, okay, to a point here. So I'm iterating, and the first time I get out of the triangle if my starting point was the point JL. Okay. So now recall the definition of Q of JL. It was defined as the product from k greater or equal than 0 of Q, oh no, sorry, this is yes, of E2 minus epsilon cubed, the indicator of JL plus V1K, and if K is 0, that means the summation is set up to be 0, but the expectation of this times this thing, okay. So if it's a white dot, you put this thing. If it's not, you don't put. But it's the expectation of this. Okay. So what you can do is that you can just use this formula to rewrite up to this point. Okay. So I want to use this formula so to get to this point, and I put outside the stuff that I know that should be outside the triangle. So when I get to outside the triangle, maybe I just got to another triangle, maybe it's a white point. So I still have to figure out if once I got out of the triangle, if I hit a white or a dot or a black point. And that's where this condition gets into play. This condition will say that with a certain high probability I'm hitting actually a white point, and therefore I can use the same calculations as in case 1. Okay, so this will be the expectation. So just iterating, so I'm just truncating this up to r minus 1. So let me write in exponential form. So it will be x of minus epsilon cubed, sum of I equals 1 to r minus 1, 1 W JL plus V1I. Yes, close exponential. And then you would have the product from k equals r to infinity. But if you realize that's just another copy of Q, but with a different starting point, which is this guy. Yes. And that outside term here just vanished because oh, we didn't have this outside term, sorry. This outside term was in the iteration, in the recursive formula, not in the actual definition, sorry. Yeah. So this was the definition, sorry for that term. And then you just truncate up to r minus 1, the product, and then since we have an exponential, it becomes a sum. And then the rest, to realize that's just another copy of Q, but translated by V1R. Okay, so what you do is that, well, we don't know nothing about these points, but we do know something about this, and this is less than 1, so just throw it away. Okay. Okay, slight technical problem. So we do have here, just drop this term, and then we use this recurrence formula, and we get that this is this stuff, oh, it's supposed to be this stuff inside, plus V1R. So let's estimate the stuff inside here. So this is epsilon cubed, this plus V1R, and then the expectation of Q of JL plus V1R plus hold, which you can just write as V1R plus 1. Okay, so now we're going to use the bound. This is going to be, well, exactly the same computations here, but instead of having J here, we're going to have J1R plus 1. So this would be less or equal than M to the minus A, QM minus 1. And now this guy here, epsilon cubed 1 JL plus V1R, and then in here we have expectation of E to O of A J1R plus 1 log M over M. Okay. So I want to remove this plus 1 this plus 1 now or later? Now let me remove this. I want to remove this plus 1 here, but not me remove this now. Let me remove it later. Okay, so this was exactly the same computation as before, which we can do here. So then we conclude that Q of JL is less or equal than the expectation of this. Okay, yes, the expectation of this. Yes, it would be an expectation of an expectation, which you can just put in a single expectation. So now, let me pull this M A here, Q M minus 1, and now we have expectation of each cube of 1W of JL plus V1R. That's good. And then we just put this thing inside, which would be e to O of A of log M over M of J1 R plus 1. Okay, so now we just need to show that, let me call this quantity here B. This will be quantity B. Now we just need to show that B, for M sufficiently large and epsilon sufficiently small, B is less than 1. That's what we need to show. So let me erase that part there. Here. Okay. So now the question is B less or equal than 1. Okay. So what we're going to use now, we're going to use the inequality e to minus theta is less or equal than 1 minus some constant of theta, let's say c of theta, for theta small. Okay. Yes. So then if we use that in here, and in this thing, so theta would be this guy here. So if we use that, we would conclude that B is less or equal than the expectation of the exponential of O of A log M over M J1 R plus 1 minus some constant C epsilon cube, and then will just be the expectation of 1, the characteristic function of something, which is just the probability. Okay. That's what we have. Great, and now we will remove this R plus 1. So what you can do is just, remember that R is a random variable, so this is not, you can think of splitting this in a product of independent variables, but this is not because we have the random variable here that's telling what's up to what point you have to summate this independent variables J's. So, but if once you choose R, you can compute the expectation conditional to choosing R equals something, and then you can remove the last one. So by using that an expectation of, if you just have one copy, and we did that. I mean at least a comment about it. This if is 1 plus little o of 1,
for m large. Okay, so if m is sufficiently large, comparable to, so let's say m greater or equal to some ca, I can make this thing to be anything very close to 1. So 1 plus little 1. Okay. And this little 1 of 1 here is with respect to m. So let me put m here. Okay. So using this, you can replace this guy here and just put 1 plus little m of 1 and then expectation of the rest. So you can go back to J1R. So what's the idea? The idea is to show that this guy here, this part here, when m is sufficiently large, this is very close to 1, and that this thing here is bounded from below. So if this thing is bounded from below, and this is it can be sufficiently close to 1 when m goes to infinity, so when I fix epsilon and send m to infinity, I will get here 1 minus delta, which would be the c times the lower bound for that, some delta times epsilon cubed. So if epsilon is sufficiently small compared to this numerical, this will be numerical, this will be bounded from below by some numerical constant. So epsilon is sufficiently small, and then m is sufficiently large compared to a and epsilon, then this will be less than 1. So we only so first we will show that this is close to 1 and this is bounded from below, and then next this is bounded from below. Okay. So now note the following. So note that JL plus V1R. So this is a random variable that takes values into the set such that J is, maybe I should write it like this. It's always in the gamma lattice, but gamma set of points. But this is J prime greater than J, and it's greater than J, of course, and L prime greater than L delta. Why is that the case? Because we know that we chose R to be exactly the first point, so that L plus L1R is greater than L delta. So so that's why it's L delta there. Okay. So next, and then recall that we define S. Well, is there? S is L delta minus L. So if I get the J prime L prime in this set, I know that the probability of JL plus V1R to be J prime L prime, and that by lemma 32 is, we can bound that this has an exponential decay. And if you plug in the variables, well, if I just move this guy to that side, it would be J prime minus J and L prime minus L. And then you can later bound by this, because this will be smaller. Then C, we have to divide here by square root of S. And then this is GS, some small c, G prime minus J minus S over 4. Okay, so just plug in lemma 32, and that's that exponential tail bound. Okay. Then what you do, you just summate in L prime, so you sum in L prime greater than L delta, and then you get that the probability of J1R be equal to J prime minus J, which is just move J1R as the first component of V1R, will be 1 over S and GS
of C. Just repeat that. Okay. Yeah, in here it should be L prime minus L, but if you want to, a larger upper bound would be just L prime minus L delta, since L delta is greater than L. That's why there is L delta here. Okay. Okay, so we have this. Now you summate over all these things, and so now knowing this, you can compute expectation. So you can compute the expectation of this, because you know the probabilities, and these are all the values that it can be, because this has to be greater or equal than has to be greater or equal than 0 than 1. So by knowing this, you know all the values, because any j prime can be j bigger than j. So you can just use this estimate. So let's say replace this this guy here by j prime prime, and this will be j prime prime. So you can just summate in j prime prime, multiplying by the values j prime prime, the value that this can have. So then you can compute this thing. What I'm saying is that you can just open this computation and compute it as the definition of expectation, and just use this estimate, and you compute that this is less or equal than 1 plus O of AS log of M over M. And here it comes the definition, why the choice, because we chose up this guy here, which was weird, but as I mentioned, it would cancel with the log M over M that showed up. So if we multiply, then it cancels, you get an extra M. So this will be 1 plus O of A divided by log M. So again, this is very close to 1. So if M is very sufficiently large, this will be bounded by something very close to 1. And we had something also multiply here, which was very close to 1, depending on M. So now all it remains to show is to show that this thing is bounded from below. Okay, by a numerical value. And then by taking M and sufficiently large and epsilon sufficiently small, B would be less or equal than 1. And that would finish case 2. So let me erase that slide. So I'm going to bound this probability here. To bound this from below, if I can show that a certain event which has probability uniformly bounded from below implies that JL plus V1R is white, then I bound this from below. Okay, so and the event is that JL plus V1R is J plus S over 4 plus O square root of S, and then L delta plus O1. Okay, so these guys here will be the J prime, and this will be the L prime. Okay, so I will show that this event here implies if M is large, implies that this point is white. So this would imply that JL plus V1R is white. Okay, so let me show that. So then I just have to measure how much probability I have for this event. Okay, and that will be a problem. It's not hard, and the idea is to use what? Yeah, the idea is to use this guy here. Very good. Star. So problem. use star to show, so this guy here, to show that the probability of, let me call this event here event E, and the probability of E is bounded from below by a numerical constant. Okay, and all you have to do is to use, not this is not star. Star is this guy here, the full guy, which comes directly from the lemma 32. Okay, so from lemma 32 we have this. That is the J prime L prime. So you just go ahead and substitute in all the things, and then you do the calculation and you compute that. You show that this is bounded from below. Okay. This is just one of those boring computations that take a long time, but you have to do it. Okay, so by using this, by this problem, I just have to make sure that E implies this. Therefore, the probability of this guy being white is bounded from below by the probability of E, which is bounded from below by a numerical constant. Okay, so what do we know? We know that, so suppose that J prime and L prime is this. What we do know? We do know that J prime is greater than J and L prime is greater than L delta. But we do know that J and L belongs to, and J and L belongs to the triangle. Okay, so I can use that. So that was that. That is the thing that log 9 plus L delta minus L log 2 is less or equal than S delta. Okay, that's what we know. But this guy here is the guy which we define by S. So from this we get that it's less or equal than S delta minus S. Okay, so then the picture you need to have in mind is the following. We have my point here JL, and my guy J prime, L prime maybe is here. So what I will show is that the distance from this line, which is the L delta line, horizontal line, this is O of 1. And then that the distance from this guy to this point here, or maybe this guy is here and the projection is already here, and then that will be they won't have this part, but it could have. And this bit here is also O of 1. Okay? So therefore that will show that the distance of J prime L prime to the triangle is O of 1. Okay? So that's my goal. And then we conclude that this guy will have to be white if M is big and big enough. Okay? What's L prime? So we already know that L prime, which is this guy, minus L delta, okay, by definition, L prime minus L delta is O of 1. So we already know this by the choice of the range that I want to estimate. Okay. And again, just to make clear why I'm choosing this is related with lemma 32 itself. In lemma 32, we concluded that basically JL plus V1R was approximately the uniform distribution in this range, okay, once S is given. So that's why we are using this range, okay. That was the heuristic idea that came from lemma 32, which I made a comment about. That's why we're doing that. Okay, so now we just have to deal with this guy here. So then what we do is the following, we just add the S over 4 here, log 9, and then, this is a log 2. Then we have S delta minus, and this will be S times log 2 minus what? A quarter log 9. And just happens that this is a positive number, so let me call this alpha, which is some positive number. Okay, And now we have what? We have j plus s over 4, but j plus s over 4 is by, this is j prime. So j plus s over 4 is just j prime minus o of square root of s. So this would be j prime minus j delta minus o of square root of s log 9 less or equal than s delta minus some alpha s. So I can move this guy to the right. So let me erase this, and it will carry a o. So let me see. So we conclude this. Okay. So what is this guy? Well, this is exactly if I consider. So if I consider this point here, this point here is bigger than j. The first component is bigger than j delta, and the second component is exactly L delta. So this left hand side is me trying to figure out if this point is in the triangle or not. So if that was true, that would mean that this point here is in the triangle, okay? And if I put some O here, that would be this close. But this thing, note that we have a square root here, we have an s. So if s is sufficiently, so when s gets larger, this would eventually be negative, and I could just bound by s delta, okay? So there is only a finite range depending only on alpha. So this is actually, you could say then, this is just O of 1, okay, because we have s here and square root of s, okay. So you conclude that. First of all, that j prime L prime. Well, L prime is greater than L delta, so it's definitely, this point is definitely not in the triangle, but it's close to it because this is O of 1 is O of 1. So this, you could say something like, in a very loose way, you could say this, that j prime is not in the triangle, but is O of 1 from the triangle. But we proved the lemma that whenever you have something like this, if the distance, if this O of 1, so if epsilon is small, so that O of 1 is less or equal than some little c log of 1 over epsilon. So that would mean that our point is closer than log of 1 over epsilon to the triangle, but not in the triangle. And we proved the lemma, which I think was lemma 31. That shows that the point has to be white. Okay. Again, if epsilon is sufficiently small, so in this case it was epsilon on n. So if epsilon is sufficiently small, then I can guarantee that the point is white. So therefore this event implies that event, and therefore this is bounded from below, and then from what I said. So we concluded if I take epsilon small and m big, then b is less or equal than 1. Actually less than 1. Great. So this completes case 2. And for case 3, that will be your reading problem. Another reading problem. Case 3 is that suppose that you have a point JL but we are not in this range. We were in the opposite range, so this would be the case where I am in a triangle, but I am in this lower part here. And then we would, the renewal process would take a while to get out. So instead of just stopping at the first possible white, you have to get a bunch of whites. So probably you have a bunch of other triangles here, and you store it actually here, and then you have to get a white here, and then you have to go back and get another white here, and then maybe another white. So that's what we have to do, and there isn't much. Well, there is some probabilistic structure you have to prove, which is which Tao does, but there isn't much of a new idea here. I mean, it's just working through the ideas already established. So that would be a problem to finish. So that would be like a reading problem. So you just read, it's not something, you just read to understand. Finish case 3. Read from pages 41 to 49 of Tao's paper. And I'm using a slightly different notation just because I'm presenting on the board, but the dictionary here to help a little bit. I'm using R as a random variable. He's using K, bold. He always using bold letters here, so it's bold, little k. I'm using V1J. He's using little v, and with this notation. So using this notation instead of this for summation. I'm using capital J for the geom4. He's using bold, little j, and I'm using this sign, and he's using this. Okay. Okay. And then you can finish case 3, and that will finish the whole result. So I hope you enjoy. This was a very technical paper. That's why lots of lectures about it. But we'll finish here, and then we'll move on to some less technical and shorter results.